Today we're going to be looking at graphing linear motion. So we have three different ways we'll look at this. First, let's get a little bit of background. What we want to be doing is thinking about, and I'll color code these things. So green, I'm going to do for displacement. But we have three key things we're going to be looking at. Displacement, and then we're looking at velocity. That's going to be purple. And displacement's units was meters. We'll use that as an example. Velocity is going to be meters per second. And acceleration we'll do in blue, and that's going to be meters per second, or meters per second squared. So every second something is changing a certain amount of meters per second. The slope, as review, is the rise over the run, or the change in y over the change in x. And the area, when we find the area of something, that's the base times the height, or if you're finding a triangle, it's 1/2 the base times the height. And again, these are our little background concepts that hopefully you're a little bit familiar with, but if not, these things will help you. So there's three keys when it comes to graphing linear motion that have really helped me over time. One is knowing, what does a point on the line actually mean? The second one is, what does the slope of the line represent? And the third one is, underneath that slope, that curve, there's some area. And so what does that area represent on a given graph? So let's jot those down. So one, what does a point on the curve represent? We need to know that. Second, what does the slope represent? So we want to know what the slope represents of that curve. And then area, what does the area represent? And we'll see that slope sometimes is a little bit tricky. We have to use a concept called tangent when it's not a straight line. So let's start out now with displacement versus time. Displacement versus time here. And we'll do a few examples. And again, displacement is how far you are from where you initially started. So it's not total distance traveled, but how far you are from where you started. So displacement, the y units are going to be in meters. The x units are going to be in seconds. And displacement's all going to be green for us here. And we'll put some points down on this line. And let's start by thinking about, what does a point on a displacement time graph mean? At the end of each time period, so you have a given time period on your x-axis there, and then we'll put a few, label this y a little bit, you're at some given location. So in this one, the object is at the same location. So when we have a horizontal line on a displacement versus time graph here, we can see that the slope is the rise over the run. So the rise is meters, the run is seconds. The units of meters per second is velocity. And here we have this horizontal line, so the slope is 0, so our object is not moving. But the key is knowing that the rise over the run is the rise units of meters, the run units of seconds. Meters per second is telling us velocity. So now let's look at the area. The area here is the base times the height. The base is in seconds, the height's in meters. And seconds, meters doesn't tell us anything. So the area, what does this mean underneath the area of a displacement time? Not really anything. There's not too much info that is really important for in the displacement versus time. Let's get another little example here. Again, we're looking at the point, the slope, and the area underneath. Those are our key features here. And we'll put some units on there. So 3 seconds, and then we'll say it moves 3 meters, and now it's not horizontal. So what do these points represent? At the end of each time, period, the object is, what's it doing? It's getting a little bit further away, right? At the end of 1 second, it's 1 meter. End of 2 seconds, it's 2 meters. End of 3 seconds, it's 3 meters away. So The point is the displacement at a given time. Now let's look at what the slope means. The slope, the rise units are meters, the run units are seconds. So meters over second tells us the velocity. And if we calculated that out and we said the rise was 1, the run is 1, then it is 1 over 1, which is 1 meter per second. That object is moving at 1 meter per second. That's the velocity, and that's what the slope told us of that displacement versus time. So the slope, the object is moving at constant velocity of 1 meter per second. Sorry, my picture's getting a little bit crooked here. I hopefully try to straighten that out. The area underneath, so remember we have a triangle now. To find the area of a triangle is 1/2 the base times the height. So that's 1/2 of the base of 3, the height of 3 meters, which is going to give us 4.5 meters seconds. Now the important thing here is not the 4.5, but the meters seconds. What does meter second mean? It doesn't mean anything really. So that's not really something that we need to find. The area underneath the displacement time graph, still not really important to us in terms of getting information. So now we have a downsloped graph. The last one was an upslope graph, which got us that positive velocity. Now we have a downsloped graph, and put a few points on there. Again, the point along the slope is the displacement at a given time. And if we label a few of these, we'll do a few above in the positives, 1 at 0, and then 1 underneath. The point 1 is furthest away. Point 2, you're getting closer back to the starting position. 3, you're back at the starting position because you're back at 0 displacement. Whereas 4, you're now going backwards. Okay, so each of those points tell us we're getting a little bit closer back to our origin, where we started. And if we calculate the slope here, the rise over the run, we have the rise of 1 over the run of 1. But that 1, the rise is negative. It's going downwards if you kind of think about it like a vector. So it's negative 1 over 1. So that's negative 1 meters per second. That velocity is negative. So that slope here is negative. We have a negative velocity. It's moving backward at 1 meter per second squared, which is why it was moving back towards the origin, because it's moving backwards. The velocity is negative. The area, again, 1/2 base times the height, so 1/2 seconds meters, still is not really telling us anything, so the area is not super important on the displacement time graph. We'll just keep reminding ourselves, area under displacement time graph not meaning a ton, slope is telling us velocity. We have this guy now who's falling, the force of gravity is going down, velocity is going down, acceleration is going down, but then he turns on his boosters. So now the force is going up from those boosters. He's accelerating upwards, but his velocity is still going down for a minute. That is what we are going to graph now with our next example. Our next type of displacement versus time graph. And we'll see since the force is going up, the acceleration's going up. This is positive acceleration. Again, displacement versus time. So we have our 3 questions. Question 1, always about the point on the curve. It's the object's location at a given time period. So we see our guy is getting closer to the ground here. And as time goes on, so by 4 seconds, he's very, very close at point C there. At 5 seconds, he's starting to move backwards. And then at 6 seconds, he's going upwards again. He's actually moving up past 4 seconds. He's moving upwards from 4 seconds all the way through 6 seconds. But the key things here, the slope is not straight, so the velocity is changing. And whenever we have changing velocity, that means we're accelerating. So this is a positive acceleration graph that we have going on. Positive acceleration graph. And the slope, it's a little bit tricky because it's not just a straight line. So we have to draw these lines that are tangent at the given points to calculate what the slope is. And tangent may be a concept you want to look up if you're not super familiar with that. You pretty much just try to draw a line without touching any point on the line but the point that you are concerned about. So the velocity is found at points tangent, and this is a downward slope here. So this is a negative velocity, and this is a downward slope. So this is a negative velocity. also. And then at point C, this is a horizontal slope. So this here, we're not moving. We've stopped moving. And then at point Z, so velocity there is 0. At point D and E, we have our 2 tangent points. Now we got these upward slopes, so these are positive velocities here. Positive velocities. We got a little velocity and then a big velocity at the end. So at point A, we had a big negative velocity. He's going down. And then his boosters kick on. The force starts going up. The velocity's going down. Acceleration's going up. But then as he starts going downwards, now we have a smaller velocity going down. And by the time he gets to 0, there's no velocity. And as he starts moving upward, now the velocity's going up. Okay, from 4 to 6 seconds there. So this is saying that the acceleration is always going up because his negative velocity slowly became more and more positive. It's positive acceleration the entire time, even though the velocity at the beginning was negative. So good thing to know, the velocity was always moving in the positive direction. So the area underneath, though, is still nothing. The area underneath is still nothing. And that you can just refer back to those last 3, that meters second doesn't mean much for us. So let's analyze this graph just a little bit. In the first half of the graph, the object is falling back to its origin, to 0 meters there. But at a decreasing rate, because it's going from a negative big velocity to a negative small velocity because a force is slowing it down, right? The rocket's pushing it up. The acceleration is in the opposite direction of the force. Oh, sorry, the acceleration is in the direction of the force. That would be wrong. Yeah, the acceleration is in the direction of the force. Acceleration is always in the direction of the force for us. Now let's look at the second half. Okay, and the second half of the graph, the object starts at 0 meters per second, and we're going to see its horizontal slope there, right? And eventually we're going to get to a really big velocity, and it starts moving much faster by point E. It's near vertical slope, shows us it's moving very fast. This is because the force changing the object's velocity continuously generates an upward acceleration, right? We have a positive acceleration this entire time. This would be like a consistent positive acceleration throughout the course of this entire time period. So we'll just color code a few things here. And now we'll look at our next little concept, okay? So we got displacement versus time again. And now, if upward facing graph was positive acceleration, this downward facing graph, now we're going to have negative acceleration. So I'll put a few time periods on here. The midpoint's going to be at 7 seconds. So now we have this object that has a continual negative acceleration from our beginning to end. So now we have this ball that's hit upward. So the velocity's up at the beginning, but the force is going down from gravity and the acceleration's down from gravity. And as it moves up, the velocity's still going upwards and the force and acceleration are still going down. And at the top point, there's no velocity. Force and acceleration are still down. And by the end, we have force and acceleration going down and velocity is very big by that very last point. So we'll just think now about this ball that is flying up in the air and coming back down to the earth. And so let's write in our tangent, our slopes here at each one of these points, A, B, C, D, and E. Try to color code those a little bit. So at point A here, we got this upward velocity and downward force, downward acceleration. So that's a positive slope again at B, right? Upward facing slope, but it's not quite as steep there, so it's a smaller velocity. And then by the time we get to C there, look, we got this horizontal line. So horizontal means it's not moving, so the velocity is 0, so it's just force and acceleration going down. Now at point D here, we have our velocity going downwards. We have a negative slope that's seen, that's negative velocity. And at point E, we have a big negative velocity, force acceleration still going down, and velocity going down, we got that negative slope. So we have this ball that is essentially in space, it's going straight up and down. And this is showing our negative acceleration. So again, this is just a ball going straight up and down. So now let's analyze what's going on a little bit in the first half and in the second half of this graph. Our ball at the very beginning, it starts moving upward with a large velocity. Okay, so you imagine you hit it with the bat, it's going its fastest, going upwards right as it comes off that bat. But the force of gravity and thus the acceleration are in the opposite direction of the movement. So force and acceleration are going down while the ball is going upward. So the ball is slowing the entire time it goes upward until it finally comes to a stop at the very top and there's no acceleration going upward. Then it starts moving downwards again. So now velocity starts moving in the same direction as force and acceleration. So then by the time we get to E, so downward with acceleration of gravity, by point E, the ball is moving rapidly downward with a negative velocity due to gravity, right? That's G, that negative acceleration due to gravity. So there's our nice little analysis of what's going on here of a ball going straight up and straight down. And then we'll color code all of our velocity and acceleration things. Velocity again for me, I'm trying to do that in purple. So a point, that's the displacement at a given time interval. So we can look at any time interval, how far away from the origin is that ball? So we see the ball's going upwards and then coming straight down. Doesn't matter that it looks like the ball is moving on the curve. In space is what we want to keep track of. It's just going straight up and down. So the slope is the velocity at the point tangent to the curve. And we just looked at that. Now the area, again, is still base times height, seconds times meters, and a second meter doesn't really mean much for us, so area we're not doing much with.